Okay, so our next stop in the tour of carboxylic acid derivatives. Now, you've probably noticed in my videos up to this point, my pronunciation's been all over the dang place on these compounds, and that's because the pronunciation of these things seems to be all over the place. I think all are correct. I've heard amide, I've heard amide, I've heard amide. I will probably continue to mix these up, and you're welcome to use whichever one feels the best to you. Of the carboxylic acid derivatives that we've considered, the amides are the most stable. Therefore, we can make them from all of the other carboxylic acid derivatives. And so we've seen the aminolysis reactions in the videos so far for the acid chlorides, the acid anhydrides, and the esters. The most popular way to make amides is from the acid chloride and the corresponding amine. Remember that we need two equivalents of the amine, one to make the amide and the other one to neutralize the HCl that's produced as a byproduct of the reaction. We can convert the amides back to carboxylic acids through hydrolysis reactions. We can do that under both acidic and basic conditions. This reaction is relatively slow, and so it must be done at high temperatures. Because the product of this reaction, when we lose the amine as a leaving group, because we're in acidic conditions, that's going to be protonated to make the ammonium ion. And because this is a bad nucleophile, the products are actually favored at equilibrium. Because this is such a bad nucleophile, the reaction tends not to run in reverse, as is the case that we saw in the Fischer esterification and the hydrolysis of esters. So this tends to be a one-way reaction. So the mechanism is exactly the same as we saw for the hydrolysis of esters under acidic conditions. We have a proton transfer, nucleophilic attack, two proton transfers to convert our leaving group into a good leaving group. We then lose that leaving group, and then a proton transfer to get rid of the charge in our product. So because we're in acidic conditions, we have to start with a proton transfer. Then we can have a nucleophilic attack, and it avoids creating the negative charge that would have happened if we hadn't started with a proton transfer. We want to lose the amine as a leaving group, but in order to do that, we need to protonate it, turn it into a good leaving group. Right? We can't just pop this guy off, because that would be NH2 minus, and I can't make a strong base when I have acidic conditions. So first I need to deprotonate this guy so I don't put two positive charges on the compound. Then I can protonate my amine. It will then fall off as a leaving group. I then have this positive intermediate that's close to the product. To get my final product, I just need to deprotonate that. If we do that with the ammonia that we created when we lost the leaving group, that forms the NH4+, that is not a good nucleophile, and so we won't get the reverse reaction. In the last video, we saw that esters could be hydrolyzed under both acidic and basic conditions. The same thing is true for the amides. And because we're going to be producing a carboxylic acid, when we do that under basic conditions, we're actually going to form the carboxylate ion. And so we need the acid workup so that we get the neutral carboxylic acid. And the mechanism is just like the one that we saw for the base catalyzed hydrolysis of an ester. Because we're in basic conditions, we don't need to start with a proton transfer, so we can jump right in with the nucleophilic attack. Now, because we're in basic conditions, there's no problem with the NH2 minus coming off as a leaving group, so I don't need proton transfers to convert that into a good leaving group. Now, because we're in such basic conditions and we have all these hydroxides and these NH2 minuses floating around, the carboxylic acid is not stable, and so it will be deprotonated to give us the carboxylate ion. And so then we need another separate step where we add a proton source. To give us the carboxylic acid. So pretty much all the reactions we've seen in this video, we've either seen before, as in the production of the amides, or the hydrolysis reactions were exactly analogous to the hydrolysis of the esters. The reduction of the amides is where we have difference between the previous reductions that we've seen. When we had the acid halides and acid anhydrides and the esters, when we reacted those with lithium aluminum hydride, that gave us the primary alcohol. In the case of these amides, when we react those with a lithium aluminum hydride, we actually produce the primary amines instead. And so this mechanism is actually quite different, and we're not going to look at that. And the product is also different than the reduction of the other carboxylic acid derivatives.